Hello, I'm Daniel Young, and this is the circuit associated with our magnetic levitation device. Essentially, it has three components: the sensing component, the control component, and the coil component. The sensing component is pretty simple. It just is an LED and photodiode combo. The LED just has a resistor connected to the LED, and the photodiode has a resistor on either side such that we can have two Vouts, one positive and one negative. And this is to compensate for the fact that one of our controllers takes in negative voltage compared to the other one. So, yeah. Our control, we decided to use PD control for our device. So D control is pretty simple. It's just a capacitor-resistor combo in this set. P control is a little more complex. We have a set point that's associated with 5 volts. We actually have a double 10K pot there just for precision. And then we have a capacitor to average out the voltage, and just this standard P component here. This outputs a pretty steady voltage that has fast recovery for it, and that worked really well for our project. Now we move on to the coil component. First we have a non-inverting amplifier, which amplifies our voltage by a factor of about 5, and that'll get us the correct voltage we need to suspend it about an inch below the actual coil. Then we have 2 power resistors in parallel just to give some current to it, and we have the coil itself. The coil itself has about 1,000 turns, and is then just connected to ground. And that's our circuit.
Hi, my name is Michael Searing, and this is our desired control behavior, or what we want our control system to do for our circuit. So on these plots, we have black, which is our set point, which is the position that we want our magnet to be at. We have blue, which is the actual position of the magnet that we're reading. These are just made-up values. And the red is what we want that specific part of the control system to do. So if you look at our P control, then you can see that the power that the P control supplies, the red, is proportional to the distance of the blue line to the black line. So this is a fairly simple one. And then when we move on to D control, it gets a little bit more complicated, because the D control is going to take the change in blue, the change in the position of the magnet, and that corresponds to the output. So as the magnet is dropping, then we want D control to supply a positive red to have it go up, to have it stop dropping. And then as the slope goes up, we want it to drop more. And the actual D magnitude depends on how quickly the magnet is rising or falling. And when we combine these, when we add together the red components, the 2 control systems, then we will get our final PD control. And this, ideally, will help us to control the magnet in a very steady way.
Hi, I'm Emily Guthrie, and I'm here to talk about the relationship between current and displacement. We needed to talk about this relationship because originally we discussed doing an alternating current method and then decided on the direct current method, and this mathematical model helped us decide why that would be a better option. The first thing is this free body diagram, which discusses the 3 forces that act on the magnet when it's stationary, the levitating magnet. The first is the stationary magnet that's placed at the top of our system. The second is the force of the coil. Both of those are magnetic forces, and here is the force of gravity on that magnet. To find these at equilibrium, we set a net force equation equal to 0, where there's no acceleration. And then to find the magnitude of the force coil and the force of the stationary magnet, we looked at the equation, the magnetic moment of the levitating magnet times dV dx, and then calculated what the B field generated off the coil and then the stationary magnet would be, which are these 2 equations respectively. Looking at the order of magnitude of these 2, we find where our first problem ends up coming from having just the alternating current method. The order of magnitude of the B field off the coil is r squared over r squared plus x squared to the 3/2, and the order of magnitude of the stationary magnet is 1 over x to the 3rd. When you end up taking the derivative of both of these, there's still that discrepancy between the 2, and when we took the derivative and plugged it into the net force equation up here and solved for current, this is the equation that we got. Plugging that equation in and graphing it for the displacement values as a result, or current as a result of the displacement values, this is what we get, which makes sense because there's an x value in the bottom of the, in the denominator, why there's an asymptote here at 0. However, it's interesting because we end up running to the point where when current is equal to 0, that's the equilibrium of the entire system, where mg is equal to the stationary magnet, so there's no need for the coil. Also, this entire equation, all of these points are places where equilibrium can be maintained when the current is at that value. As you'll see in the actual report where we took the log of the absolute value of current and plotted that as a graph, there's an actual point where at the equilibrium the forces are, the current has to spike up in both directions, which you can kind of see here, the amount that current has to fluctuate around this equilibrium point, which proves why the alternating current method wasn't a good idea. We would have had to have maintained this point at equilibrium where the current was equal to 0, and then the current would have to fluctuate a lot for any form of displacement at all. Instead, it makes more sense to place our displacement somewhere further away from the stationary magnet where current can fluctuate only a certain amount, which makes our control system a little bit more effective.
Oh, we got that one. That's all we need.